Look up at night and you see a tiny fraction of our local neighborhood. But zoom out past our solar system, past the edges of the Milky Way, and you enter the observable universe, a space containing an estimated 2 trillion galaxies. The sheer math of it makes a sterile cosmos difficult to imagine. The Drake equation organizes that math. It breaks the massive question of alien civilizations into measurable fractions: the rate of star formation, the number of habitable planets, and the fraction that develop life. Multiply them together, and you get an estimate of active communicating civilizations in our galaxy right now. Astronomer Frank Drake wrote this out in 1961 during a conference at the Green Bank Observatory in West Virginia. It gave scientists a way to frame our ignorance and start quantifying the unknown. Since then, our understanding of habitability has widened. On Earth, we've found microbes thriving in deep ocean trenches, boiling acid springs, and even the vacuum of space. These extremophiles prove that liquid water and an energy source are often all biology needs to take hold. Organic chemistry is universal, and life is resilient. If the ingredients are present across the cosmos, then the biology we see here should be repeating elsewhere, which leads to a very uncomfortable problem. In 1950, physicist Enrico Fermi was having lunch with colleagues when he pointed out a flaw in the math. If life is so common and the universe is nearly 14 billion years old, civilization should have had plenty of time to spread. So he simply asked, "Where is everybody?" For over 60 years, we have pointed massive radio telescopes like Arecibo at the stars, listening for any structured transmission, and the result has been absolute static. This absolute lack of detectable signals is known as the Great Silence. It creates a brutal tension in modern astronomy. The models say the galaxy should be crowded, but our instruments detect a ghost town. Waiting for a radio call hasn't worked. To resolve the contradiction, science has had to shift strategies, moving away from passive listening and toward actively hunting for physical and chemical fingerprints. The search begins next door. Mars is a frozen desert today, but we know it once had oceans. Rovers are currently exploring dried riverbeds, and they've detected seasonal spikes in atmospheric methane. On Earth, most methane is produced by living organisms, making these seasonal releases prime targets in the hunt for microbes. We already have physical pieces of Mars to study. In 1996, scientists examined a Martian meteorite found in Antarctica and noticed tiny tube-like structures resembling fossilized bacteria. The findings remain highly disputed, highlighting exactly how difficult it is to verify alien biology from a rock. Beyond Mars, we are looking at the icy moons of Jupiter and Saturn. Europa and Enceladus hide massive saltwater oceans beneath their frozen surfaces. Probes have even captured massive geysers erupting from Enceladus, venting hydrogen and complex organic compounds directly into space. To get definitive proof, we need pristine samples. NASA's Perseverance rover is currently packing tubes of Martian dirt and rock. A planned 2033 return mission will bring those exact samples back to labs here on Earth for rigorous testing. Finding even a single dead microbe on Mars or in a plume from Enceladus answers the biggest question. It would mean life on Earth isn't a fluke. It would mean biology is a standard feature of the universe. Our own solar system is just a tiny sample size. Astronomers have now confirmed over 5,000 exoplanets orbiting other stars. Since we can't send rovers 40 light-years away, we have to look for biosignatures, specific gases in their atmospheres that living things leave behind. Our primary tool for this is the James Webb Space Telescope. Its massive array of mirrors is sensitive enough to capture the faint infrared light passing through the atmosphere of a planet trillions of miles away. This graph shows how that light splits into a spectrum. Different molecules absorb different wavelengths of light, creating dark gaps in the spectrum. Recently, researchers saw a potential gap corresponding to dimethyl sulfide, DMS, on a distant water world. On Earth, DMS is produced almost exclusively by marine life. We are still waiting for verification on that specific molecule, but the method works. We can effectively see the chemical breathing of a biosphere across interstellar space. Sometimes the search yields anomalies that refuse to be categorized. In 1977, a radio telescope in Ohio picked up a 72-second burst of radio waves. It was exactly at the 1420 megahertz frequency, the hydrogen line, which scientists predict an intelligent species would use to communicate. It has never repeated, and it remains a compelling, unverified technosignature. Closer to home, military tracking systems have recorded objects demonstrating impossible physics. The Navy's famous Tic Tac encounter involved an object dropping thousands of feet in seconds, showing no visible means of propulsion and outmaneuvering fighter jets. These sightings pushed the U.S. government into a rare moment of public transparency. In 2023, former intelligence officer David Grush gave sworn testimony to a congressional committee, claiming the government had recovered non-human biologics and craft. Testimonies are not peer-reviewed data. However, the radar tracks and thermal videos from trained pilots present a specific physical mystery that modern science cannot yet explain. We are now tracking objects operating far past current human engineering limits. If intelligent life exists, the math demands to know why the galaxy is so quiet. This diagram shows Nick Bostrom's Great Filter, a theoretical barrier stopping civilizations from expanding. Have we passed it, or is it waiting for us? This is why finding microbes on Mars would be a grim discovery. It means the barrier is likely ahead of us. A civilization-ending filter could take many forms. It might be a cosmic event, like a nearby supernova, or a self-inflicted bottleneck, like nuclear annihilation, extreme climate collapse, or uncontrollable artificial intelligence. The Fermi paradox serves as a mirror for our own trajectory. When we search for alien civilizations, we are looking for evidence that a technological species can survive its own development. Here is the scientific consensus as it stands today. Based on the math and the chemical makeup of the universe, basic life likely exists. Whether any of it builds radio towers or spaceships remains entirely unproven. But the tools to find out are finally online. Between the Webb telescope analyzing atmospheres, missions heading to Europa, and rocks returning from Mars, the next 20 years of data will map the local neighborhood like never before. The data coming back from Mars and the icy moons will resolve the silence. Whether we find neighbors or a profound solitude, the discovery will define our identity in the universe.